Hello, and welcome to chapter 11. We're going to be going over rolling, torque, and angular momentum. So, we're going to identify that smooth rolling can be considered as a combination of pure translation and pure rotation. We're going to apply the relationship between the center of mass speed and the angular speed of a body in smooth rolling. So we consider only objects that roll smoothly, no slip. That complicates matters. The center of mass of an object moves in a straight line parallel to the surface. The object rotates around the center of mass as it moves, and the rotational motion, which you've probably seen by now, is the arc length is going to be equal to the angle multiplied by the radius. You may have seen that equation expressed as theta is equal to S over R before now, but here it's written a little differently. So the velocity of the center of mass is going to be the same as the angular velocity multiplied by the radius. And here you can see the picture. There's S, there's the angle subtended, and you can see the motion of the center of mass here. So you can see here in this particular figure how the velocities of the translation and rotation combine at different points on the wheel. So here you can see that the velocity is going to be the same as the minus velocity of the center of mass. The direction is just different. Up here at the top, you're going to see that the velocity of the center of mass is going to be the same as the velocity of that point on the wheel. This is considered to be pure rotational motion of the wheel. And then you can see the angular velocity defined there. If you look at pure translation, the velocity of the center of mass, the velocity of point P and the velocity of point T, everything is going to be the same. It's going to be pointing in this particular direction. Now, if you add those two together, for the rolling motion, which is going to be rotation plus translation, you're going to see the velocity at the top point is going to be the same as 2 times the velocity of the center of mass. The center of mass is going to be moving in this direction, and P is going to have no movement at all because this was minus the velocity of the center of mass. This was the velocity of the center of mass. You add the two together, you get 0. So the roller wheel on a clown's bicycle has twice the radius of the front wheel. We've got some, I think that's supposed to be rear wheel and that's supposed to be front wheel. So we got some typos in here. When the bicycle is moving, is the linear speed at the very top of the rear wheel greater than, less than, or the same as that of the very top of the front wheel? So when a bike is moving, is linear speed at the very top of the rear wheel greater than, less than, or the same as the very top of the front wheel? And it turns out it happens to be the same. Is the angular speed of the rear wheel greater than, less than, or the same as that of the front wheel? Again, remember that this has twice the radius of the front wheel. If we go and look at the angular speed here, remember that the angular speed times the radius is going to be the same as the velocity of the center of mass. So the velocity of the center of mass, if we look at the very top of the wheel for each one of those, the velocity of the center of mass is going to be the same. However, if we have a larger radius on the rear wheel, which has twice the radius of the front wheel, then that would mean that the angular velocity is going to be less than the angular speed of the front wheel in order to be able to compensate. The angular velocity is going to work inversely to the radius. If the radius becomes bigger, then the angular velocity has to become smaller. So forces and kinetic energy of rolling. So we're going to combine translational and rotational kinetic energy. When that happens, the kinetic energy is going to become 1/2 times the moment of inertia, the center of mass, times the angular velocity squared, plus 1/2 times the mass of the object times the velocity of the center of mass squared. So you're seeing the rotational energy there on the left side of the right side of the equation. And then the translational kinetic energy is going to be on the right side. So if a wheel accelerates, its angular speed is going to change. And a force must act in order to prevent slippage. That force is going to happen to be friction, the static friction force. So just like with what we had here before, where we had the length and then the velocity was proportional to the radius by the angle and then the angular velocity. Here, the acceleration of the center of mass is going to be equal to the angular acceleration times the radius. So if a slip occurs, then the motion is not considered to be smooth rolling. So for smooth rolling down a ramp, the gravitational force is vertically down, no surprise there. The normal force is perpendicular to the ramp, and the force of friction points up the slope because this ball is rolling down. So this is attempting to resist that particular progress. If we zoom in on the picture here, kind of see things a little bit better. This gravitational force, if we look at it in the angle it makes with the normal force, we can see that this is f sub g cosine of theta. We can see that this is fg of sine of theta. We can see that these two forces determine the linear acceleration down the ramp, and these two forces balance each other. And the torque due to the static friction determines the angular acceleration around the center of mass. We can use this specific equation to find the acceleration of such a body. Note that the frictional force produces the rotation, and without that, the object is just simply going to slide. What would cause the angular acceleration? There wouldn't be anything because there's no force being applied. So in order to accelerate it, you have to have a force applied to it. Okay, so discs A and B are identical and roll across the floor with equal speeds. Then disc A rolls up an incline, reaching a maximum height h, and disc B moves up an incline that is identical, except that it is frictionless. Is the maximum height reached by disc B greater than, less than, or equal to h? So in thinking about this, the maximum height reached by B is going to be less than that reached by A. For A, all of the kinetic energy becomes potential energy at h. Since the ramp is frictionless, for B, all of the rotational kinetic energy stays rotational, and only the translational kinetic energy becomes potential energy at its maximum height. So now let us consider the yo-yo. As a yo-yo moves down a string, it loses potential energy because its height is decreasing, but does gain rotational and translational kinetic energy. So if we're going to find the linear acceleration of a yo-yo accelerating down its string, we're going to look at this as if it rolls down a ramp of angle 90 degrees. As it rolls on an axle instead of its outer surface. It's rolling on an inner surface. And it's slowed by tension in the string rather than friction. So you can kind of see the free body diagram here. You've got gravity and then you've got tension pulling up. So if you replace the values in equation 1110, then it will give you this particular value. And if you go through and you calculate the acceleration of a yo-yo, if its mass is 150 grams, it has a radius of 3 millimeters, and the moment of inertia of the center of mass is equal to this. Plug all of that in, then you can find the acceleration of the center of mass. All right. We're going to go back and we're going to look at torque again. So previously, torque was defined only for a rotating body at a fixed axis. And now we're going to redefine it for an individual particle that moves along any path relative to the fixed point. The path does not need to be in a circle. We're going to consider torque to be a vector. And the direction is going to be determined with the right-hand rule. And if you're not familiar with the right-hand rule, there are several places out there for you to be able to go and to look for it. Basically, you're going to be crossing vectors. And if I zoom in here, as you are crossing certain vectors, torque is going to be the radius cross force. You're going to have certain rotations that you do with your hand. The first vector here, R, is going to be your thumb on the right hand. The force is going to be your index finger. And then you can look at it if you extend your middle finger out, or if you look at the direction of the palm of your hand, that tells you where the torque is pointed. So again, the R is going to be your thumb, F is going to be your aligned along the force, R cross F, and then torque is going to be in the direction of the palm of your hand. So as I just finished talking about, the general equation for torque is going to be R cross F. You can also write that in magnitude as RF times the sine of the angle between them. Or if you know the perpendicular component of force or the moment arm, then torque is going to be equal to R times F that is perpendicular, that perpendicular component, or torque is equal to the radius that is perpendicular there to the force. I do believe part C here may have an error in it. If you run the right-hand rule for this particular problem, you do it yourself and you let me know. So the position vector R of a particle points along the positive direction of a z-axis. Let me see how well I can draw this. So I'm going to say a z-axis is up like that. And I'm going to say y-axis is like over here. And then I'm going to say that the x-axis is over here. And now all of these are going to be considered positive. So let me positive y, and then put this here, positive z. Okay, so this is our set of axes. If the torque, well, let's go back to this. Position vector R of a particle points along the positive direction of the z-axis. So we're going to say that's pointing up. So this would be, go ahead and draw this again. So R goes up that way. In this particular case, this is the direction that your thumb would point. The position vector R point of a particle points along the positive direction of a z-axis. If the torque of the particle is 0, in what direction is the force causing the torque? If your torque on the particle is going to be 0, then according to the definition that we had earlier of torque, then that out again. R is pointing this way. Torque would be the way that your palm would point, but in this particular case, it ends up being 0. And the reason for that is another way to look at this is RF sine of theta. We know there's a position vector R. We know that there's a force. So the only thing that's going to make that torque 0 is that the sine of the angle there for part A is going to be 0. And the only way the sine of an angle is going to be 0 is if that angle itself is 0 or if it's 180. So in that particular case, your force is going to be either along the z-axis, the positive z-axis, and the minus z-axis. One of those two. Now let's look at part B. If the torque is in the negative direction of z, it's going to be pointing that way. So the palm of your hand would be pointing in the negative x direction, so it's going to be like that. So imagine taking your palm and pointing it away from you. And then you take your thumb, point it up along the z-axis. Which way does your index finger point? And it should point in the positive y direction. If you look at part C, if the palm of your hand is pointing in the negative direction of y, which means it would be pointing this way, and the position vector points up along the z-axis, then which direction is the force causing the torque? And this is where I disagree with what it has here. It says in the positive x direction. I believe it's going to be the negative x direction because your index finger would point this way. Try it out for yourself. See if you think I'm wrong. So calculating net torque. You can look at several different combinations here, where you've got A, B, C, D, and E here. You've got R coming up this way. You've got force this way, force this way, force this way. This is your particular setup here. So we've got, if we're looking at F1 here, F1 is pointing in this particular direction. You've got R pointing this way. If you're going to cross R into F1, which is how this is read in this particular book, the torque is into the figure. In other words, your z-axis is this way, your x-axis is this way. So that basically they've taken this particular picture and flattened it out so that this surface is right here. If you do that and you curl your fingers such as this, R curls towards F, which way does your thumb point? It points into the page, which is, in this particular case, going to be in the negative y direction. If you look at part C here, if you take R and it's being subjected to force 2, if you take, again, your, I guess will be your right hand, and then you fold it towards this particular force, which way does your thumb point? Your thumb points out of the page here. If you take the final vector here, F3, out of this particular drawing, and again, remember the X and the Z are graphed in this fashion, so how do we represent force 3? We have to represent it by it pointing into the page, and that's why you see that X there for that particular vector. So you're going to take R and you're going to align your hand on it. You're going to fold it towards the force, which is basically you're curling your hand up. I'm sorry, curling your hand down. The way they've got this, why would you have your hand this way and then have it this way? That's a little strange. You would take your hand and curl it this way, and that means your thumb points in this particular direction. So this is the 3 torques out of having your arm, this lever arm out here, and having those 3 forces on it. These are your torque vectors that result from that. Angular momentum. Up to this point, we've seen where several different components of linear motion can be have an analogous a counterpart when it comes to rotational motion, and momentum is no different. So how does one compute angular momentum? What do you have to do? Well, angular momentum is going to be the same thing as r cross p. So if you take your vector r and you cross it with the momentum vector, you can rewrite this. Since mass doesn't depend on its position, it can sort of be factored out of the momentum here. Remember, momentum is going to be your mass times the velocity. So that m comes out here at the front. It's just r cross v. So notice that the particle doesn't need to rotate around O to have angular momentum. And the units of angular momentum is going to be kilogram meter squared per second, or joules per second, or joules seconds, sorry. So let's say we have certain momentum heading this way. We have a lever arm out here. If we take r cross p, this is a drawing of how that is performed. And then if you're going to do r cross p, you're going to want to take the perpendicular component of this and multiply those two together. Another way to do that is to take the perpendicular radius that lies exactly perpendicular to the momentum. Either one of these, if you'll remember the equation back, you're taking the perpendicular component of one to the other, be it first to the second or second to the first, it doesn't matter. So to find the direction of angular momentum, we're going to use the right-hand rule to relate r to v. To find the magnitude, use the equation for the magnitude of a cross product. So you're looking at r times m times v. It would have been better if they'd had the m out there in the front, but they didn't do that because they wanted to keep you thinking about momentum. But you're looking at the sine of the angle between r and v. Or, however, if you are looking at just the perpendicular components, you can write it in the fashion of these two equations. So, angular momentum has meaning only with respect to a specified origin. It is always perpendicular to the plane formed by the position and linear momentum vectors. So we're going to take a look here at this figure right here. Well, we've got a force or a particle moving this way and another particle moving this way. It's moving around in circles with a radius of 2 millimeters and 4 millimeters. So this point here is 2 millimeters away from O. This is going to be 4 millimeters away from O. In part B, particles 3 and 4 travel along straight lines at perpendicular distances of 4 meters and 2 meters from point O. So this is going to be 2 meters away. That's going to be 4 meters away. Again, those are perpendicular distances. Particle 5 moves directly away from O. And all 5 particles have the same mass and the same constant speed. So m and v for all of those are going to be the same. So rank the particles according to the magnitudes of angular momentum, of their angular momentum around point O with the greatest first, and then which particles have negative angular momentum around point O. Negative angular momentum. That's, you got to keep direction in mind. So let's take a look at this. If we're going to be looking at R cross V for the angular momentum, the masses are all the same, so that doesn't matter. So we're looking at R cross V. The way you maximize that is you have the bigger radius, and that's going to give you your answer as far as which one's going to be the greatest, because the velocity is always going to be the same for every point. So the ones that are going to have the maximum perpendicular distance away from your axis of rotation are the ones that are going to have the most angular momentum. And in this particular problem, that's going to be, of course, 1 and 3. The perpendicular distance that is greatest next is going to be 2 and then 4. 5 brings up the end there because its distance is not considered perpendicular here. It's just straight away. So the second part of this, which particles have negative angular momentum around point O, it turns out to be 2 and 3. Now, you may be thinking, well, why is that? If you look at this, if you take the, you can use the right-hand rule and have your R point in the direction, or your thumb point in the direction of R, your index finger point in the direction of the vector, which if you look at problem or point number 1, your thumb would follow from O to 1, your index finger would point out to the left, and that means your palm would be up. That indicates a positive angular momentum. If you look at it for number 2, if your thumb were to follow from point O to 2, your index finger would point out again to the left, but your palm would be pointing down. And that would mean you would have a negative angular momentum. If you look at point 3, where you would have, let's see, your thumb would point up, your index finger would point out to the right, which means your palm would point down. If you look at point 4, your thumb would point down, your index finger would point out to the right, and if you're not contorted by now, then you're not really following along. Then the palm would actually point up for point 4. So, and since this doesn't have angular momentum, then just 2 and 3 would be your final answers. So, Newton's second law in angular form. We've seen what it is in linear form, but what about angular form? Well, with angular form, or with linear form, we had force is equal to the change in linear momentum with respect to time. The analogy holds if you look at angular forms of that. Your torque is going to be your force in an angular sense, and that is going to be the derivative of your angular momentum, represented with L, with respect to time. So the torque and the angular momentum must be defined with respect to the same point, usually the origin. The vector sum of all of the torques acting on a particle is equal to the time rate of change of the angular momentum of that particle. Just finished discussing there. Again, look at the similarity here to the linear form, where the net force is going to be equal to the change in momentum with respect to time. So let's take a look at this checkpoint. So the figure shows the position vector r of a particle at a certain instant. And you have four choices for the direction of a force that is to accelerate the particle. All of those lie in the xy plane. There's no z vector that goes along with that. So rank the choices according to the magnitude of the time rate of change they produce in the angular momentum of the particle around the point O with the greatest first, and which choice results in a negative rate of change about O. Well, all of the force magnitudes are going to be the same. In other words, F1, F2, F3, F4, all of the magnitudes of those particular forces are going to be the same. The only question is which produce the greatest angular momentum. Now, again, remember your definition of angular momentum. Not so much the torque there. That's not really what we're looking for. What we're looking here for is angular momentum is going to be RMV sine of theta. Now, for this particular problem, R is going to be the same. The mass is going to be the same in each problem. So what we're looking at is the direction of the force or the direction of the change here in momentum. And we're going to be looking at the sine of the angle between those two. Force 3 is going to end up being perpendicular here, since everything lies in the xy plane. That's going to be perpendicular to R. Since that's going to be perpendicular to R, that is going to produce the angle that has the greatest value of the sine of that particular angle. So if we're looking at the magnitude of that change in angular momentum, F3 is going to be our best bet. We're going to apply a force that is perpendicular to that arm of R. F1 is going to be our next best bet. While it is not perpendicular to that particular arm, it is at an angle. It is at an angle away. If it were not at an angle away, such as with forces 2 and 4, the sine of the angle between those, we're either taking the sine of 0 in the case of F2, or we're taking the sine of 180 in the case of F4. Both of those would lead to a 0 result. That's why they end up dead last. So force 1, which makes some angle between 0 and 90 for R, is going to be in the middle. part B here, which choice results in a negative rate of change, about 0? Obviously, we're going to throw out 2 and 4. That's not going to do anything for us. If we try the right-hand rule, and we'll go ahead and do it here for force 3, if we look at how that's going to be applied, if I place my thumb along the along the I wish you guys could see this, but if you're placing your thumb along this line and then your index finger there, if you try doing that on your own, your palm is going to be facing the computer screen, and because of that, it's going to be pointing in a negative x direction, and that means that you're going to have a negative rate of change because it's going to be pointing in a negative z direction. Angular momentum of a rigid body. So the sum of the angular momenta of the particles, or we sum the angular momenta of the particles to find the angular momentum of a system of particles. So in other words, you got all your particles out there. Each one of them has some sort of linear momentum. If you sum all of them together, then you get the sum of the angular momentum of all the particles and of that system. So the rate of change of the net angular momentum is going to be dl dt. And when you take the change with respect to time of the angular momentum, that will get you the torque. And that's going to be the torque of each one of those individual particles. So in other words, the net torque is going to be defined as the change of the system of particles' angular momentum with respect to time. And if you got a lot of particles, that's a lot of summing. The net external torque acting on a system of particles is going to be equal to the time rate of change of the system's total angular momentum. So note that the torque and angular momentum must be measured relative to the same origin. It's not really any different than forces and linear momentum being relative to the same origin, so that really hasn't changed that much. If the center of mass is accelerating, then that origin must be the center of mass. We can find the angular momentum of a rigid body through summation, which we're looking at the change of mvr, with that being perpendicular there, or the change in the mass. And if we replace v with omega times r, because that's what the definition is, if you remember that earlier on in this section, and then that's multiplied by r. And then if you take a look at this, we can factor out that angular momentum, and then we're left with the sum of the change of mr squared. If you remember, that's going to be considered your rotational inertia, or your moment of inertia. So as it turns out, your system's angular momentum is going to be the same as the moment of inertia times the angular velocity. So the presentation here gives you a correspondence here between translational and rotational, or linear and rotational, depending on how you want to look at it. These are the comparative concepts. That is a good thing to have. So here we're looking at angular momentum of a rigid body. Focusing in here, we've got change in mass here, then we've got the r stretching up to that particular point around that's from the axis. And then you have the r component that's perpendicular to that point, and then you have the momentum of that particular point. And then you can see the corresponding angular momentum of that particular point. So in the figure, you've got a disk, you've got a hoop, and you've got a solid sphere. And they are all made to spin about a fixed central axis, like a top, by means of strings wrapped around them, with the strings producing the same constant tangential force on all three objects. Three objects of the same mass and radius, and they arc initially stationary. Rank the objects according to their angular momentum around their central axis. And their angular speed, greatest first, when the strings have been pulled for a certain time. So the answer to part A, ranking their angular momentum around the central axis, all the angular momentum is going to be the same because the torque is the same in each case. In other words, the strings produce the same constant tangential force, or the torque. That's going to be the same for all three of the objects, since we are looking at torque being the change in the linear momentum, or the angular momentum here. That might come into play here a little bit, but what you are looking at here is this torque is going to be the change in the moment of inertia times the angular momentum. Where that's going to come into play is going to be their angular speed, greatest first, when the strings have been pulled away from a certain time. In order to be able to do that particular problem, you're going to need to know the moment of inertia for the sphere, for the hoop, and the disk. And that is why they are in the order that they are. The angular speed of the sphere turns out to be the greatest, followed by the disk, and followed by the hoop. The reason for that is when you look at the definition of angular momentum, the moment of inertia for each of those is going to be different. It's going to be different, and what you're going to find out is that since the sphere is going to have the greatest angular speed, that is because it has the least, the lowest moment of inertia of all of those. And then the disk is going to have a higher value for the moment of inertia, and the hoop is going to have the highest of all of them. So that is why they are ranked, and if you wish, you can go and you can look up the moment of inertia for each of those and try that out for yourself. Conservation of angular momentum. When no external net torque acts on a system along a specified axis, apply the conservation of angular momentum to relate the initial angular momentum value along that axis to the value at a later instant. What that essentially means is that the linear momentum you start out with is going to be the same as what you end with. If you have an isolated system, then your angular momentum is going to be considered to be constant. There is no net external torque on the system. If the net external torque acting on the system is zero, then the angular momentum of the system remains constant no matter what changes take place within the system. Since they are vector quantities, they are equivalent to the three corresponding scalar equations, and that means you can separate the axes and write that if the component of the net external torque along the system along a central axis is zero, then the component of the angular momentum along that axis cannot change no matter what changes take place in the system. So the moment of inertia times the angular momentum initially And again, I think we got another typo here. And it's going to be the same as the moment of inertia as it exists at a later point in time times the angular momentum of that later time. Those two quantities are going to be equal. So, for example, you've got a student spinning on a stool. The rotation speeds up when the arms are brought in, slows down when arms are extended because angular momentum is conserved. A springboard diver. Rotational speed is controlled by tucking your arms and legs in, which reduces rotational inertia and increases rotational speed. A long jumper, the angular momentum caused by the torque during the initial jump can be transferred to the rotation of the arms by windmilling them, keeping the jumper upright. So this is an interesting problem. A rhinoceros beetle rides the rim of a small disc that rotates like a merry-go-round. So if the beetle crawls towards the center of the disc, which of the following increase, decrease, or remain the same for this beetle disc system? Each, of course, relative to the central axis. The rotational inertia, the angular momentum, and the angular speed. The key to this particular problem is the angular momentum. There is no net external torque to this system. Because of that, the angular momentum is going to remain the same for each one of these before as well as after. What's going to happen to the rotational inertia and what's going to happen to the angular speed? Well, the angular speed is going to increase. And why does the angular speed increase? Let's go all the way back here. What's happening here to the radius? The radius of that thing is beginning to get smaller. Because of that, angular velocity of that particular beetle is going to increase. When that increases, that's also going to affect the rotational inertia. That rotational inertia means that that beetle is also no longer further out in the merry-go-round. It's further in. And if you'll remember, the rotational inertia, the moment of inertia, depends on how that mass is distributed. And if it's closer to the center, that means the rotational inertia is going to decrease. In order to keep the same angular momentum, if that decreases, then the other, which multiplied together produces the angular momentum, must also increase. Procession of a gyroscope. I don't know if you've ever played with any of these. They're kind of cool. A non-spinning gyroscope right here, if you were to put, you've got some support here with an axis going up here, and then you've got another one coming out here, and then you've got this wheel that's sitting out here. If that wheel ain't moving, that thing is falling over. But if you start to rotate the wheel, this thing will start to rotate around the axis. This rotation is called a precession. So let's zoom in on that a little bit here. So you've got the support here, you've got the R coming out here, and then you've got gravity. If this thing is not rotating, then this thing has no other option other than just to fall. If, however, you give it a little bit of a rotation here, this thing starts to move, and it starts to move around in this way, in this fashion. And you can see it here. This is going to be the circular path taken by the head of that angular momentum vector. So the angular momentum of a rapidly spinning gyroscope is going to be the same as what we've seen before. The torque can change only the direction of L and not its magnitude. Reason being, I mean, torque is defined as the change in the angular momentum divided by the time. If you bring that over here, this is the equation that you end up with. The only way its direction can change along the direction of the torque without its magnitude changing is if it rotates around the central axis. So therefore, it precesses as opposed to toppling over. The precession rate is going to be given by omega is equal to mgr divided by the angular momentum. And this is going to hold true for a sufficiently rapid spin rate. It's going to be independent of mass, but not the gravity. And it's going to be valid for a gyroscope at any angle to the horizontal as well, like a top. All right, we'll go over the summary here. You've got a good picture of it. Again, this is going to be posted as well. If you do have any questions, please do let me know.